Solution equilibrium. Welcome to lesson 5. This goes along with the SE4 and 5 assignment on maximum dissolvable amount. You're going to be introduced to the green sheet as well as the KSP expression. When a solution is saturated and there is also solid at the bottom of the beaker, the amount of solid does not change. Although the chunk of solid doesn't appear to be doing anything, there is still action on the surface. Solid still dissolves, but since the solution is saturated, every atom that dissolves into solution forces another atom to fall out of solution and join the solid at the bottom of the beaker. Here we have BaCl2 solid sitting on the bottom of the beaker. Ba2 plus and Cl minus continue to dissolve into the solution, but at the same time, the Ba2 plus and Cl minus ions that are dissolved in solution continue to add to the crystal. I want you to add the two particles, the two arrows, and the chunks of solid to the diagram that you find in your handout. Since the reaction is going both ways, and the amount of solid that is dissolving equals the amount of aqueous that is precipitating, the system is said to be in equilibrium. The general equation for the system is AxBy in equilibrium with X amount of cations plus Y amount of anions. X and Y are the numbers used to balance the charge in the ionic formula and elements in the decomposition reaction. Our example is aluminum sulfide. 2 aluminums gives us a +6 charge. 3 sulfides give us a -6 charge. Those numbers that were used to balance out the ionic formula are also found in the decomposition reaction. To find the amount of solid that will dissolve in water, we use the KSP values from the list of solubility equilibrium constants on the green sheet, and they are related by this equation. KSP equals concentration of products divided by concentration of reactants. Now, two things before we go on. Number one, this is on your pink sheet, sort of. You have the KQ expression here, which is KQ equals concentration of products over concentration of reactants. I also want you to make a note that square brackets mean concentration. You can add this note to your green sheet, maybe add it to your pink sheet, maybe put it down on the piece of paper where you're going to be taking down the examples. Now, if we go back to that generalized formula, we said KSP equals concentration of products, which are the cations and the anions, over top of the concentration of the reactants. Now, two things to note about this. Both a cation and anion have been raised to the power of whatever numbers were used to balance out the cations and anions in the decomposition reaction. The second thing to note is that the reactants in KSP will always be eliminated, and that's because solids do not have a concentration. Solids and liquids do not have concentrations and will always be eliminated from equilibrium expressions. This then simplifies our expression in this unit to KSP equals concentration of cations to the power of whatever number was used to balance them in the decomposition reaction, multiplied by the concentration of the anions, also raised to the power of the number used to balance the anions in the decomposition reaction. So what is the KSP expression for Ag3PO4? Well, the first thing I always do is make a decomposition reaction. So KSP will equal the cations to the power of 3 multiplied by the phosphate concentration divided by Ag3PO4. Which, as we said, will be eliminated because it is a solid. So the KSP expression is then simplified to simply KSP equals silver ion concentration cubed multiplied by the phosphate concentration. So the KSP equals the silver ion concentration cubed multiplied by the phosphate concentration. And if I look on the green sheet, I find that the KSP equals 2.6 times 10 to the negative 18. Yes, that green sheet that you've been given in class. We look up silver phosphate and we find out that silver phosphate has a KSP value of 2.6 times 10 to the negative 18. So what does that mean? Well, this number will help tell us the maximum amount of silver phosphate that can be added to a water sample. If the silver ion concentration cubed multiplied by phosphate concentration is less than the number on the green sheet, that means I have not yet reached the maximum dissolvable amount, because that's what I call the number on the green sheet, our maximum dissolvable amount. So if the concentrations we have added are less than a maximum dissolvable amount, we can still dissolve more silver ions, we can still dissolve more phosphate ions into solution. But if the silver ion concentration cubed multiplied by the phosphate concentration is equal to the maximum dissolvable amount, that number on the green sheet, then that means the solution is saturated. Adding any more silver ion or phosphate ion would result in solids forming at the bottom of the beaker. And in a case where our silver ion concentration cubed multiplied by our phosphate ion concentration is larger than the maximum dissolvable amount, that number on the green sheet, that means the water has had more silver ions and phosphate ions added to it than it can hold. There is going to be solid sitting on the bottom of the beaker and the solution will be completely saturated. Example 1, what is the KSP expression for calcium hydroxide? I make my balanced decomp reaction. KSP will then equal the calcium concentration multiplied by the hydroxide concentration squared. That's my cation times my anion. Either one is raised to whatever number was used to balance in the balanced decomp reaction. So what is the KSP expression for calcium phosphate? Again, I do my balanced decomp reaction. My KSP will equal the calcium concentration to the power of 3 multiplied by the phosphate concentration to the power of 2. Example 3, calculate the aluminum ion and hydroxide concentrations when aluminum hydroxide has been added to water until the solution has become saturated. The first thing we do is write our balanced decomp reaction for the solid, which would be aluminum hydroxide breaking up into aluminum ions and 3 hydroxide ions. Now I want you to leave a little bit of a space below here because we're going to add some numbers in there afterwards. So down a few lines, we'll write the KSP expression. And KSP equals aluminum concentration times the hydroxide concentration cubed. Now, we don't know how much Al3 plus we're going to have in the end. We don't know how much OH minus we're going to have in the end. And we don't even know how much aluminum hydroxide we're going to be adding to the water. So we don't know how much of this we're adding. But we do know if I add 1 aluminum hydroxide, it makes 1 aluminum. So if I add X amount of aluminum hydroxide, it will make X amount of aluminum ion. And for every aluminum hydroxide that's added to water, it makes 3 hydroxide ions. So if I added X amount of aluminum hydroxide, it's going to make 3X amount of hydroxide. So when we're done, the Al3 plus concentration will equal X, and the hydroxide concentration will equal 3X. So why don't we sub those in? Al3 plus equals X, and hydroxide concentration equals 3X. And notice I carried the cube down because the cubed came from the KSP expression. On the left side of the equation, well, let's utilize that green sheet. So I go to the green sheet and I look up aluminum hydroxide. That tells me that aluminum hydroxide has a KSP value of 3.0 times 10 to the negative 34. I'd like for you to, in your notes, make a note that that number came from the green sheet. Because when you look back in your notes, you're probably going to forget that. So I took 3x and I cubed it. So 3x times 3x times 3x gives me 27x cubed. I will then multiply that by x, and that will give me 27x to the 4. Now I'm going to isolate x. I start by dividing both sides by 27, and I wind up with x to the power of 4 is equal to 1.1 repeating times 10 to the negative 35. Now I have to take the fourth root of both sides. That gives me x equal to 1.8257 times 10 to the negative 9. I encourage you to punch that into your calculator to make sure that you are carrying this procedure out properly. If you don't get this answer, well, we got to figure that out before you go on to the assignment, because if you get it wrong here, you're going to get it wrong continuously when you do the assignment. Now we can sub these back in. We said the aluminum ion concentration equals X. So the aluminum ion concentration equals 1.8 times 10 to the negative 9 molar. Only 2 sig figs because, well, this is all multiplication and division, and our green sheet has limited us to 2 significant figures. Hydroxide concentration is equal to 3x. So I'm going to take my answer that I got, X of 1.8257 times 10 to the negative 9, multiplied by 3, and then correct it to 2 significant figures, and that gives me 5.5 times 10 to the negative 9 molar. Now that was a good time, so let's do it again. Example 4, calculate the silver ion concentration and the sulfate concentration when silver sulfate has been added to water until the solution becomes saturated. Again, we start off by writing our balanced decomp reaction. Leave a little bit of a space, and we're going to write our KSP expression below that. So KSP equals concentration of silver ion squared multiplied by the sulfate ion concentration. Make sure that KSP expression is written properly because I'm going to put marks on that when I'm marking your assignments. So again, we don't know how much silver ion or sulfate will be added, but we do know it's coming from some undetermined amount of silver sulfate being added. So if I add X amount of silver sulfate, it will produce 2x amount of silver ion and X amount of sulfate ion. So when we are done, the silver ion concentration will equal 2x and the sulfate concentration will equal X amount. And we can sub those in. So silver ion will equal 2x, and again that squared carries down from the KSP expression, and that will be multiplied by the sulfate concentration, which is equal to X. We can get the KSP number off the green sheet, so I find silver sulfate, oh, there it is, 1.5 times 10 to the negative 5, and I will sub that in for KSP. Now I'm going to start off by doing the 2x squared. So 2x squared is equal to 2x times 2x, which gives us 4x squared. And 4x squared multiplied by x gives us 4x cubed. Now to isolate x, I'll divide both sides by 4. And that gives me x to the power of 3 is equal to 3.75 times 10 to the negative 6. When I cube root both sides, I wind up with x equal to 1.55 times 10 to the negative 2. Now let's sub that back in. So Ag plus is equal to 2 times that amount. So I multiply that number by 2 and correct it to significant figures. Concentration of silver ion is then 3.1 times 10 to the negative 2 molar. The sulfate concentration is equal to the value of x. So the concentration of sulfate is 1.6 times 10 to the negative 2 molar. And that's the end of the lesson. It's time to start working on that SE4 and 5. Another one in the books. Good work.